video, we'll continue with module 4.3, significant figures. So significant figures tells us the number of digits in a measurement, because we're always doing measurements in the chemistry lab, that are known with some level of error or uncertainty, because every time you make a measurement, there's an error in the machine. There's also error in the person doing the experiment. So we introduce these significant figures, and there are rules that we need to follow. So we just go through examples. So every time there's a non-zero digit, we consider them significant. So in this case, 1.55 has 3 significant figures. We can say sig figs. Number 2, all zeros embedded between non-zeros are significant. So these zeros here in 1.003, it's 4 significant figures. Trailing zeros in a number with a decimal place are significant. So 1.000 is 4 significant figures. 1000 is 1 significant figure. These zeros in 1000 are not. However, if we had 1000 dot, that would be 4 significant figures if we added a decimal there. Leading zeros are not significant. So in this case, 0.00305 is 3 significant figures. 3, 0, and 5 are significant. So for each of the values below, you can pause it here. Let me know how many significant figures each one is. So in this case, 100.0 is 4 significant figures. 1, 2, 3, 4. 60.1 is 3 significant figures. 0.001 might be a bit tricky, but it's only 1 significant figure. And 1.003 is 4 significant figures. So once we establish how many significant figures are in a value, we have rules for multiplying and dividing numbers, and we have rules for adding and subtracting numbers. First, when you add or subtract, the rule states that the answer is based on the smallest number of decimal places. So in this example, 1.003 plus 0.2 plus 0.001, the first step is to figure out how many decimal places are in each number. This one has 3. 1, 2, 3 decimal places. The next one has 1 decimal place, so I'll put 1 decimal place. And the next one has 1, 2, 3 decimal places. And according to our rule, our answer should have the same number as the smallest one in the question. So in this question, the one that with the least decimal places is this value here. So your answer will also have 1 decimal place. So 1.003 plus 0.2 plus 0.001 will come out to 1.2 grams, 1 decimal place. A different rule for multiplying and dividing, it's based on the number of significant figures, the least number. So in this case, we have 4 sig figs, we have 1 sig fig, and before even doing the calculation, you know the answer will have 1 sig fig. So 1.002 times 0.005, if you do that on the calculator, it actually comes out to 0.00501. But because we just said the least amount of sig figs will be in your answer, this will come out to 0.005. And again, because the lowest sig figs in the question is 1 sig fig, therefore your answer should have 1 sig fig. I'll ask you to pause the video now, and I want you to try on your own to the correct number of significant figures. So the first one, we're back, is 5.0 grams divided by 0.31 milliliters. This will come out to 16 grams per milliliter. Again, 2 sig figs in the question. So therefore our answer should have 2 sig figs. The next one, 15.0, which is 3 sig figs, times 0.003, which is 1 sig fig. And when we do that, we get 0.045. However, we want our answer to be to 1 sig fig because this one is the least when we're multiplying and dividing. So our answer will be 1 sig fig, which comes out to 0.05. This would be meters squared as a unit. We're rounding up because this number is 5 or greater. This number rounds up to 0.5. Our next example is an adding or subtracting. So therefore we use the least amount of decimal places. So here we have 3 decimal places. We have 2 decimal places. Therefore our answer will have 2 decimal places. This comes out to 1.01 grams. And for the last one, again, we're adding and subtracting 3 decimal places and 1 decimal place. This comes out to 0.9 milliliters. And I'll let you try this one. If you did something like 3 times 9 to the correct sig figs, the answer is not 27, it's 30. Because this is 1 sig fig, and your answer needs to have 1 sig fig. So normally you would say 27, but you have to round up to 1 sig fig, so it'd be 30. So don't tell your non-chemistry friends that 3 times 9 is 30. They'll look at you a bit weird. So we'll move off significant figures and just touch a little bit about the Earth and its temperature. And we'll move into that later as well. But here we have 46% of the sun's radiation is absorbed by the Earth. There's a nice graph or a nice figure here. So 46% absorbed by the Earth. It rebounds, or it's re-emitted in the form of IR, 37% of it, into the atmosphere. And luckily we have, to some effect, we have greenhouse effects, which means that we have the atmosphere being able to absorb some of that heat. It doesn't go all the way back into space. So some of that is absorbed by greenhouse gases, and this gives us a temperature of 15 degrees average on Earth. If we didn't have our atmosphere and these greenhouse gases, the average temperature would be minus 18 degrees Celsius. But some of us know that if we have too many greenhouse effects and too many greenhouse gases, the temperature could slowly rise above 15 degrees Celsius. And we'll talk a little bit more in depth about that later. So greenhouse gases, similar idea where you grow plants, food in a greenhouse, which is a glass casing. So light shines in. It's absorbed they absorb by the plants, the light rays, and then converted to heat. And when the plants release the heat, it's actually trapped within the glass. So that is somewhat of a greenhouse effect. And inside the glass casing, the heat is conserved. There's no wind from the outside that can push that heat away. And we have the similar effect with greenhouse gases. CO2 is a greenhouse gas. Water vapor as well can be considered a greenhouse gas. And what happens is about 80% of the IR infrared radiation emitted by Earth is absorbed by these atmospheric gases. And it actually vibes, or you can say, it goes in flow with the structures. So carbon dioxide here, CO2 here, and water on the left, they absorb IR, but N2 and you can say O2 do not. And it's because of, it's a little bit beyond this course, but it's because there's no change in dipole moment for the N2 and O2. And we'll talk a little bit more in detail on the next set of slides, but here we've talked about Lewis structures, how to draw Lewis structures. And from those Lewis structures, we'll talk about the shape of molecules. So in this case, methane, which is CH4, has a shape of a tetrahedral.